So finally, let's talk about induction motors. That's the most common type. And there's a exploded view here. I'll let you look at that in more detail. I want to only point out certain parts of it. These are by far the most common type of motor. They're called a squirrel cage motor, and you'll see why that is in a moment. But there's no electrical connection to the rotor itself. So you can see the components here. You can see the rotor in the middle. That's the thing that rotates. That's the name. You can see the bearings, the housing. And then there are electrical windings in what's called the stator, or the frame. Okay, the stator is mounted to the frame technically. They're separate parts. But there's basically coils inside of the motor. And I've got some videos that you'll have to watch that are much better at animating and explaining how motors work. It was something that always seemed kind of magical to me. You know, I always tried to understand. I couldn't see anything mechanically that would make it work. We have to understand that basically these are big transformers. That's what they are. And actually the coils induce current into the squirrel cage of the motor and produce a magnetic field in the rotor that opposes the magnetic field produced in the stator, and that's what makes it turn. And so basically these are just big electromagnets, and magnets are what make motors actually go and push. That's where the force comes from, is the magnets. So you can see the squirrel cage here where the rotor laminations have been removed. The purpose of the rotor laminations is to enhance the magnetic field in it and make the motor more powerful. But then the stator, there's a section of it here. A stator is usually much longer than this, but this is just a short stator and rotor to see how all this works together. But anyway, so the squirrel cage on the left is part of the rotor, and it's just, as I said, two big electromagnets pushing on each other. That's what makes the shaft turn. What we really care about more than anything, though, in specifying a motor is the performance of the motor. What is its nature? How does it behave? So there's a few things we need to understand. If we look at a torque speed diagram where we have torque on the y-axis and speed on the x-axis, these are very common diagrams for motors. And there's some particular points that are of special interest and particular concern. One is the so-called locked rotor torque, or the starting torque. So this is the amount of torque that the motor has to develop, that the motor develops when it's at rest. And regardless of what position the motor is in, because see, actually, depending on the actual angular orientation of the rotor, more or less torque can be developed. So this is at least this much torque is developed. If you happen to be in a good place, if the rotor happens to be at the right angle, it might start and generate even more torque at the beginning, but at least in the worst position it will develop this minimum locked rotor torque. The breakdown torque is the torque, it's the farthest point on the right of the curve, and it's a unique and useful point to know, because if you think about it, if the motor, let's say the motor's operating up in the upper region of that curve, and let's say you the machine requires more and more and more torque, well, what's going to happen is the motor's going to slow down. You can see that curve slopes off and to the right, so the motor's going to slow down as it develops more and more torque, at least in your everyday garden variety motor, as if motors grow in gardens. Guess that wasn't a good analogy. And so the speed drops off as the torque increases. Well, you eventually reach a point where the motor simply cannot generate any more torque, and what happens is it reaches breakdown torque, and then the motor starts slowing down even further, down below, it looks like it'd be about 70% of full speed or so. And since the torque requirement of the machine is higher than even the breakdown torque, or even if the torque drops off, the motor will actually coast down to rest, or actually could stop very quickly. The torque could slow it down and break it, essentially, very quickly. So breakdown is sort of the point of no return. It's where it's like when you're on the weight bench and you just can't get the bar up anymore, right? You're lost. You're done. That's it. So it's the maximum torque that the motor will develop, but it's an important point because that's where the motor starts to lose, essentially. The full load torque is the torque that the motor is supposed to develop at its rated speed. Now, a motor's rated speed, there's a theoretical speed and there's a rated speed, because motors do slip, and we'll talk about that more in just a little bit. But the no load speed is all the way at zero torque. That's 100%. That's the highest speed that the motor can develop. And there's always some load on the bearings of the motor and so forth, but it's small, so you can neglect that. But this is defined as the percentage of synchronous speed. Now, what is synchronous speed? Well, let's leave that for a future slide. I'll show you what synchronous speed is. There's many different types of single-phase induction motors. What I've shown here are electrical diagrams of four. There's the shaded pole motor, and the place where this is commonly used is in your bathroom. If you have an exhaust fan in your bathroom, it's probably a shaded pole motor, and they're not particularly efficient, but they're just little cheap, easy to produce, low power motors that are very reliable, so they're in common use. You know, if you think you want to save energy by replacing all shaded pole motors with something a little better, you'll spend a lot more money and a lot more energy in making the new motors to replace all these shaded pole motors. So there's a lot of times that, you know, theoretically better things aren't actually better. There are permanent split capacitor motors, and what's that? Well, to understand why we have all these varieties, you might think, well, why don't you just power the coil and let it induce current in the rotor and let the thing go, right? You've got the stator coil, just power it up and let it go. Well, the problem is with one phase, the motor will actually not start turning. You actually have to have two phases offset from each other, provide a difference in the magnetic field so they don't just align and they basically chase each other around. So you have to have this offset field. Well, how do you generate it? Well, the shading pole, or the shading coil, does that in the so-called shaded pole motor. In the permanent split capacitor motor, what happens is there's a starting winding in series with a capacitor there across that top wire leg, and that actually generates a separate field, an offset field, that allows the rotor to start turning. So you've got the running winding and you've got the starting winding, but notice that the starting winding never comes out of the circuit. It's always there. This is not great for efficiency. Okay? There's the so-called split phase, where you have a starting winding and a running winding, but you've also got a centrifugal switch. So what happens is, as the rotor starts to move faster and faster, there's a switch mounted on it. It's a mechanical thing, where arms basically just fly out and disengage the starting winding. It pushes a switch basically as long as the motor's above a certain speed. And you'll hear these click. This is the type of motor that when you shut it off, you hear it spin down and you hear it click at some point. Sometimes you can hear it click as it comes on, but usually that's a louder thing. So the split phase is a different type of, it's a different way of providing that second field, but you don't need that field after the motor is turning. You can actually shut it off. You only need the two separate out of phase currents for the beginning, the starting of the motor. So again, the shaded pole motor is not very efficient, neither is the permanent split capacitor motor very efficient, because they never remove that extra phase, essentially, and so they're not as efficient. A capacitor start motor is actually probably the most common on decent sized motors. I'm sure your compressor in your air conditioning system has it. There's a lot of motors in your home that have this setup, but they're bigger motors, and they involve the starting winding, the starting capacitor, but now we've also got the centrifugal switch. And so you know, if you ever, I know my mom had an AC system that wasn't working right. She was elderly at the time, and so she called me and asked me if I knew what was wrong with it. It was just making funny noise and wasn't cooling her home. It was getting hot. So I went over and looked into it, and what had happened is the starting capacitor had gone bad. And I could tell because it was bulged very badly on the end. And so I simply replaced it, and that fixed the problem. You need that capacitor as sort of an extra kick to get the motor going at the beginning, but after it's going, the centrifugal switch cuts out that, or disconnects, the starting capacitor and the starting winding. Okay, so all that's great. We can learn more about how that works, why you need the second phase. Here's what we really care about. We care about the performance of these motors. So what you see is a torque speed curve for several different types of motors that generate the second phase in different ways. Okay, so now these are not exact, obviously. This is just a schematic, a general representation of how these motors behave. So you see that the shaded pole motor generates the lowest torque. The permanent split capacitor is a little better, but also, you know, again, is just marginally better than shaded pole. I shouldn't say marginally, I guess it depends on the two motors. The split phase motor has higher starting torque, and the capacitor start has, on average, the highest starting torque. Now the motor housing is something that's very important as well, and something you have to consider. There's a lot here. Let's talk about it. There's the open protected drip proof motor in the upper left hand corner. You notice there's no holes on the top of it. Well, that's so that any liquid can't get inside of the motor and damage it. But it's open. What does that mean? Well, that means the air can flow through it. One of the things that is most likely to make a motor quit working is overheating the motor. If you can cook a motor pretty quickly, and then the motor's no good because the laminations short out or the coils short out, and you don't have a motor anymore. You have a piece of metal that needs to be recycled. Some motors are capable of being rebuilt, but a lot of times that's not really practical unless you have a very large motor. So the open protected drip proof motor can be used in situations where you've got oil around. You don't want it dripping into the housing. The TENV, what does that mean? Well, it's totally enclosed non-ventilated. That's what TENV stands for. Non-ventilated, that sounds like a bad idea. It sounds like the motor will tend to overheat. Well, yeah, that's true. And you notice that cooling fins are included on the housing, the body of the motor. Why would you ever want that? Well, what if you don't want things getting into the motor at all? And there are reasons for not wanting that. In that case, the totally enclosed non-ventilated would be ideal. But of course, that type of motor would tend to overheat. So what if you add a fan on the back? Because you see, motors commonly have their shafts running through the front and the back. So there's some shaft on the back that's available, and a lot of times you simply mount a fan on that back shaft to blow air across the motor. So you see that piece of sheet metal on the rear of the totally enclosed fan-cooled motor, top row still. And the purpose of that sheet metal cover, it's a cowling. It directs the air from the fan across the fins of the motor to keep the motor cool and keep it from overheating and keep working. Now there's a variation on this. The totally enclosed fan-cooled XP stands for explosion proof. This is the kind of motor you would spec for any dusty environment. I don't remember how many years ago it was, but I believe it was in Georgia that a sugar plant exploded. Just down the river from us there was a power plant where coal dust exploded. And I don't remember how many lives were lost. I think that in the power plant no lives were lost, and in the sugar plant some lives were lost tragically, but you don't want any source of sparking. And of course electric current has potential for sparking, right? Even though there's no brushes or anything between the rotor and the windings, it's still possible for there to be something that would ignite dust, static discharge, anything like that. And so this totally enclosed explosion-proof motor not only has the housing totally enclosed where nothing can get into it, has the fan on the back, which may or may not cause a problem if there's any static. Obviously it should be designed to not generate static in the first place. But you notice the little box on the side of all these. I haven't mentioned it so far. Well, that box is where the wiring connections are made. Well, on an explosion-proof motor, that box is very carefully sealed to prevent anything from getting in there and finding a source of ignition for dust or whatever the case may be. A washdown rated motor is a little different. A washdown rated or a washdown duty motor is a motor that can safely be basically sprayed off. And so this would be, totally enclosed. You see the fan for cooling. This would be used when you're trying to process food items. So if there's a beef processing plant where a motor is used, then a washdown rated motor would be required, because occasionally you have to wash everything down, and a lot of times you're going to use relatively strong chemicals to kill off any biological or foreign matter, and so a washdown duty motor would be the choice. You notice the severe duty motor has even cooling fins on the front face of the motor, and so it has a bigger fan, and it's for applications where there's severe overheating, higher power output, those sorts of things. A brake motor, going down to the last row, has a brake mounted on the back side. Now sometimes they'll have a fan, but definitely a brake motor has a brake on it, so that when the motor is turning, a lot of times there are applications where you want to stop the motor very quickly. Well, a brake motor has a brake on the back of it. Sometimes these are set up where the brake just automatically engages and you have to provide power to disengage it because you want the motor to stop turning when power is lost. You know, that's the safe thing. Usually a brake motor is used where you've got some safety concern. So the brake motor has a brake mounted on the back of it and will stop the motor from turning very rapidly. And there's many different ways to brake a motor. Just a mechanical brake is not the only way. And then there are C-face motors. A C-face motor has a very particular front face, and you'll notice that several of these actually are similar to this. But it has a very particular bolt pattern. It's made to be bolted onto something. And of course it has a boss ring that basically just helps align the motor so that the shaft is well aligned with whatever machine it's supposed to drive. So you can have a C-face motor that's many of these designs. Totally enclosed fan-cooled explosion-proof motor could have a C-face on it. It just has more to do with the geometry and how it's mounted. You'll notice that several of these motors have so-called feet, or a section of the motor that's made for bolting down to whatever machine it's on. So I've sort of already gone through all of this. An open motor, though, has no protection. So an open motor is a type where, it's just open. There could be vent holes on the top of it, and certainly things could fall into the motor. That's the only type I really didn't talk about yet. Motor housings are standardized, and of course this is a benefit. It means that you can buy a motor from one manufacturer and then change to a different manufacturer if you wish, and the motor will just mount right up. So it's one of the few things that are standardized. I shouldn't say few things. There's a lot of things in the mechanical world that are standardized. I guess I get jealous of the electrical guys because so many of their things are so standardized you can buy from any vendor and it's pretty much the same thing. I think, though, that probably things are a little more complicated because we use more assemblies and things in the mechanical world. A motor is already an assembly, right? So it's nice to have the motor standardized because you could go get a motor from someone else if you wanted to. And as long as it follows standard housing frame sizes, then it'll mount up just fine, or at least should. Now, obviously, the performance of the motor will vary from manufacturer to manufacturer. So this is not these frame sizes are not a performance constraint; they're just a geometric constraint. Another thing to talk about is motor starters. Motor starters are a really important piece to the puzzle of speccing a motor, because when you have a motor, you have to have some way of turning it off and turning it on. You don't want it to run just all the time. And when you turn on the motor, there's a couple things you want to do. You don't want to just connect power to the motor and that's it. You need something where you can protect the motor. So if you look from the electrical supply to the motor, you'll notice that there's always some type of disconnect device. So it's something where you can basically disconnect the motor and not allow the motor to work at all. Just if you look at your AC system outside of your home, you probably have a disconnect box which can be opened up, and there's usually a little plug that can just be pulled straight out. You'll notice there's some conductors in it, and there's no way that power can get to that unit anymore because of the disconnect device. In industrial situations, often you have a box with a handle on it you can pull down. So that's the disconnect device. But then there's always branch circuit protection. What is that? Well, think of that as your breaker, like in your breaker box in your home. That's something that if too much current is flowing through the wires so that the wires are liable to fail, then the breaker shuts off or fuse shuts off. Then there are always motor control devices. These are the things that actually will turn the motor on or off, will vary the frequency to the motor or whatever is needed to control the motor speed. So things that are there to control the motor. And then finally, motor protection devices. And there's many different things that the motor needs to be protected from, but the main thing is overheating. So a lot of times there are thermal cutout switches that are built into the motor. There are current sensing switches in line with the motor so that if the motor is overloaded, whatever machine is trying to drive is, say, locked up where it can't turn, then all the current going to the motor is just heating up the motor, and you don't want the motor to overheat. So there are current overload devices. There's other things to protect the motor from. But the main thing to think of is how much current is flowing into the motor. And so a motor starter has to be made so that it matches the motor heating curve. You don't want a motor starter that is for sensing overload in a huge motor and you put it on a little bitty motor. Well, if the little bitty motor is locked, it might just be drawing what looks like a small amount of current to the large motor starter, and so the large motor starter just lets the current go and cooks the motor. So you really have to match the motor starter to the motor heating curve, and the idea is that the motor starter should keep the current to the motor below the motor heating curve. And so there's this whole current versus time thing that the motor protection device has to sense and ensure that the motor never gets too much current for too long, basically. And there's some standard motor starters for single phase power. You can see the NEMA size numbers there and their ratings and so forth.